Okay, this is our worksheet that we did. Okay, our first question, when the area in square units of an expanding circle is increasing. So there at that particular moment, notice that we're told that the area is increasing. So that tells me that we have dA over dt. And I know that because it says area of an expanding circle is increasing. Now, how is it increasing? It's increasing twice as fast as its radius. So, and then it goes on to ask us, well, what is the radius? Well, it's increasing twice as fast as the radius. So I think that's also given me some idea about the rate of change of the radius. And notice it's really telling us a relationship between the area, the rate of change of the area and the rate of change of the radius. And it's telling us that the rate at which the area of the square is increasing is twice as fast as the rate of change of the radius. So really, I know that dA over dt is equal to twice the rate that the radius is changing. So we know that. And let's see, we need a formula with some kind of related rates. We always need some formula. I know the area formula for a square is pi r squared. And when I find the derivative of area with respect to time is 1 dA dt equals 2 pi r dr dt. Now notice what it's asking us to find. We need what is the measure of the radius when this happens. So notice I do have a relationship here with dr dt in area, so I could make a substitution here. I could change dA dt with what it's equal to down here, and so that's going to give me 2 dr dt equals, and again I'm changing that out with what it's equal to down here. Let's see, 2 dr dt is equal to 2 pi r dr dt. And so notice if we start dividing things out, notice that our 2's will cancel and our dr will cancel. And so we have 1 equals pi times the radius. And we're asked, well, what is the radius? So from this equation, we see that the radius has to be 1 over pi. And there's a couple of ways to do this, but this is just the way I chose to do it. So our answer should have been C. So for number 2, we have the radius r of a sphere is increasing. So I would stop there again. We know that the radius r of a sphere is increasing. So that's telling me a rate of change for the radius is increasing at a uniform rate of 0.3 inches per second. So we have 0.3 inches per second. At the instant when the surface area becomes 100 pi, so that tells me that my surface area is 100 pi. Notice it tells us at that instant. It does not tell us that the surface area is increasing or decreasing. It's just pinpointing it at an instant. We have 100 pi. And let's see, that's inches squared. So at that instant, what is the rate of increase in cubic inches per second in the volume? So it's asking us about dV dt. What is the rate of change at that instant of the volume? Well, notice they gave us 2 particular formulas. And notice here the first one, surface area, S. Well, we've got S right here. So let's see. that's going to give us 100 pi inches squared equals 4 pi r squared. And it looks like from this we should be able to solve for r. If we divide both sides by 4 pi, that should give us 25 equals r squared. So I see pretty quick that my radius is 5. Now I would go ahead and find the derivative up here of my volume. And do remember that 4/3 pi, every bit of that is a coefficient. All of that's just a number. So when I do my derivative, then all I have to do is multiply this 3 down to the front. And so those 3's will cancel. And so I have 4 pi r squared, dr dt. Okay, so, and we're asked for the rate of change of the volume. So it looks like we can go ahead and just plug in a few things here. We need dv dt. 4 pi r squared. Well, you know, I kind of did some extra work right through here because we have this 4 pi r squared, this 4 pi r squared, and we're talking about the same sphere. So really, if I didn't want to do all that extra work, I can just substitute in right there. Let's see, dv dt is really equal to 4 pi r squared, which is 100 pi times the rate of change of the radius, which we were told was 0.3 inches per second. So it looks like we could have saved ourselves a lot of time without that extra work, but you just never know with these problems. So if I multiply those two together, it looks like I'm going to get 30 pi. So it looks like our answer choice should be E. Okay, number 3 is really more or less a classic related rates type of problem for AP Cal. We have the radius and the height of both increase at a constant rate of 1/2 centimeters per second. So I know both dH and I know dH dt is equal to dr dt. And both of those are equal to 1/2. And then I also know that the height is 9 centimeters. And I know that the radius is 6 centimeters. Now, let's see, what are we trying to find here? It looks like we're probably trying to find the rate of change of the volume. And so here's our volume problem. And you can leave 1/3 pi sitting out front and just mainly focus on, if you want to, just focus on these two variables and leave that 1/3 sitting on the outside. And that way you would have fewer numbers to work with. So when I start doing the derivative here, I know I have dv dt equals, and I'm going to leave 1/3 pi sitting out here, times, and so we're going to have to do the product rule. So we have the first times the derivative of the second, which is going to be 1 dH dt, plus the second times the derivative of the first, which is going to be 2r dr dt. And now we're ready to plug in what we do know. So let's see, we have dv dt equals 1/3 pi times our radius squared. So we're going to have 36 times the rate of change of our height, which is 1/2, plus our height, which is 9, times 2 times our radius, 12, times the rate of change of the radius, which is 1/2. And now we're ready to finish working all this out. So dv dt equals, and we have 1/3 pi times, and let's see on the inside here, looks like we get 18 plus, let's see, 9 times 6, maybe 54. And let's see, I would cancel that 1/3 with 18. Let's see, that's going to leave me a 6. And 1/3 into 54 looks like it's probably going to go, let's see, how many times? 1, maybe 18. So we have 6 plus 18. That's going to give me 24 times pi. So it looks like the rate of change of the volume is 24 pi. Okay, so for number 4, we have the area of a circular region is increasing. So again, I would stop and say, well, I know the rate of change of the area is increasing at 96 pi square meters per second. When the area of the region is 64 pi, so I know the area is 64 pi, how fast in meters per second is the radius of the region increasing? So I'm looking for dr dt. So I need to remember the area formula of a circle, pi r squared, and we need to find the derivative of this with respect to time. And let's see, that's going to give us 2 pi r dr dt. And it looks like we really have just about everything we need. We have the rate of change of the area, 96 pi equals 2 pi times the radius. We're not given the radius, but we are given the area is 64 pi. So that tells me that I think the radius is probably going to have to be 8. And then times the rate of change of the radius. And so we end up with 96 pi divided by, let's see, 16 pi. So looks like we're probably going to get 6 for our rate of change. So dr dt is going to be 6. Okay, and then number 5, we're given the sides of a rectangle. So knowing that this is a rectangle, then we know that's a right angle. And we're also, let's see, given sides x is 4 and y is 3. So if x is 4 and y is 3, then we know we have a 3, 4, 5 right triangle, and that's always useful. And we're trying to find the rate of change of dx dt, or the rate of change of x. And we're told some rate of change relationships here. And it looks like we might need to use the Pythagorean Theorem. And so I know x squared plus y squared equals z squared. And we can go through and do our derivative. And notice each time I go through and do the derivative, I do get a 2 in front of each one of those, and we end up canceling out the 2. And so I'm going to say that we have the 2, but then I'm not going to write it because we will eventually cancel it. So we have 2x dx dt, and I'm just going to write x dx dt, plus 2y dy dt, so I have dy dt, equals 2 times z dz dt, so I'm going to write z dz dt, because those 2's would cancel out of every term there. And now I'm ready pretty much to plug in the information that I have. And so let's see, x we know is 4 times dx dt, which all we know about that is that it's 3 dy dt, plus y, which is 3 times, and then we know dy dt, we don't know much about that, equals, and we know z is 5, and we know dz dt right there is 1, so I'm going to write that's all equal to 5. And so notice here I have 12 dy dt's, but then I have 3 more over here, so we can just collect our like terms and have 12 plus 3, or 15 dy dt's. equals 5, and if we divide both sides by 15, notice we have dy dt equals 1/3. And this is where we have to be super careful, because as soon as we get 1/3, everybody wants to go mark A, but that's not what we were asked. We found the rate of change of y, but we were asked, well, what is the rate of change of x? So we have to go back up and use this relationship here, that dx dt is 3 times dy dt. So 3 times 1/3 is going to give us 1. So the right answer is B. Okay, here's another classic problem. It's a ladder problem, and we normally see these coming up on the AP exam somewhere. And so we have a wall, we have a ladder, and I have awesome drawing skills, y'all. It's just amazing. We have this 25-foot ladder, and the top of the ladder is 7 feet off the ground, so I know this distance is 7 feet. And we know that the ladder is sliding down the wall, so that's our y-coordinate. And notice that this distance is really shrinking as this is moving downward. So I'm going to say that our dy dt, we're sliding downward, that's -3 feet per minute. And what do they want us to find? What is the rate of change of the distance between the bottom of the ladder and the wall? So that's wanting this distance here. So I need to know dx dt. And looking at it, this distance is growing here, so I would expect that value to be positive, because it would be increasing there, that distance. So I would automatically chunk out those two values because they're negative, and this should generate a positive value for us. So what is the rate of change in the distance at the bottom of the wall? So it looks like we have our good old Pythagorean Theorem, x squared plus y squared equals z squared. If you need to plug in and see, we can find where this side x is going to be 24. And if you need to plug in the Pythagorean Theorem to find that, go ahead. And then we also need to find the derivative of this. And just like earlier, each term is going to have a 2 in it. So I'm going to delete the 2 as I'm going through, or cancel the 2 as I'm going through this process. So let's go ahead and find that derivative, and change color so all this doesn't run together, hopefully. So I'm going to have 2x dx dt, and I wrote a y there. Let's undo that. That was terrible. Dx dt plus 2y dy dt equals 2z dz dt. And let's start filling in what we know. So we know that side length x, we found that to be 24, and again that's from the Pythagorean Theorem, times the rate of change of that side, that's what we don't know, plus, let's see, -3 times, because that's my dy dt, times that side length, so that's really going to be a -21 there, equals, and this is the other side, we know that side length is 25, but this ladder's not going to have a rate of change. We know the length of that ladder is not changing, so that's going to be 0. And so after we go through this algebra, we have dx dt equals 21 over 24, and hopefully that reduces to be 7/8. Okay, so now for number 7. Number 7, the radius of a circle is increasing at a non-zero rate. So, gosh, that doesn't tell us just a whole lot about dr dt, but we have a dr dt. At a certain instant, the rate of increase in the area of the circle is numerically equal to the rate of increase in its circumference. Okay, so again, at a certain instant, the rate of increase in the area of the circle, so dA dt, is numerically equal to the rate of increase in the circumference, so dC dt. Okay, at this instant, the radius of the circle is. So we're looking for r. I don't know what that is. Well, let's see. I know the area of a circle is pi r squared. And so if we find the derivative, we find that dA dt is 2 pi r dr dt. And let's see, the circumference. Well, the circumference of our circle should be, let's see, your circumference is pi times the diameter, but I really would like to keep these terms as similar as possible, so let's call it 2 pi r. So if we find the derivative here, dC dt, well, that's going to give us 2 pi dr dt. So now it looks like we might have some kind of relationship here that we can put together. So let's see. We know dA is equal to 2 pi r dr dt. And that's going to be equal to the rate of change of the circumference, which was 2 pi dr dt. So it looks like, let's see, 2 pi's will cancel, and dr dt's will cancel. So, gosh, there's nothing left over here but a 1. Remember, we're canceling. We're dividing out. We are not subtracting. So it looks like my radius would have to be 1. So that's going to be answer choice D. Okay, another good problem. In the triangle above, if theta increases at a constant rate of 3 radians per minute, so notice now we're talking about theta increasing. So now we're going to have d theta dt, which looks strange, but is no different than all the other problems we've been doing. It's now d theta. So d theta increases at a constant rate of 3 radians per minute. At what rate is x increasing in units per minute when x equals 3 units? So let's see, a lot of times we go ahead and we see, well, if x is 3, and again there's another 3, 4, 5 by a triangle, but we can't forget that we need some kind of formula here to find the derivative of. We need a rate of change for that angle. So that means we're going to have some kind of trig. And I would stick with what we were given, which is going to be, from this angle's point of view, I was given opposite, and I was also told the hypotenuse. So when I work on this, I would just about see opposite, hypotenuse. I would probably need sine. So I'm going to say sine of my angle. And I know sine is 3 over 5, but that's not giving me a formula. I need a variable in there. So I'm going to say it was x over 5. Now, I would also rewrite this so that that is 1/5 x. That way we see very quickly that's just a coefficient for x. And so when I do the derivative here, the derivative of sine of an angle is cosine of the angle, but this is what we tend to forget, times the derivative of that angle. And we're doing these derivatives with respect to time. So there's where we're going to use d theta dt equals, and if I do the derivative of 1/5 x, we see that that's 1/5 dx dt. We see that that's the same. Okay, now we have a formula. And again, we're looking for the rate of change of that side length, which is right here, that dx dt that I'm looking for. So let's see, we can find cosine of that angle, and that's where that 3/4/5 is going to come in useful, because cosine of theta is going to be 4/5. So I have 4/5 times the rate of change of theta with respect to time, which I was given was 3, equals 1/5 times the rate of change of x with respect to time. And so if I multiply both sides by 5 and finish working out all of this, it looks like we're going to get 12 equals dx dt. So my right answer should be E. Okay, another rate of change problem. Notice here we're told that the container has the shape of an open right circular cone. As shown above, the height of the container is 10 centimeters and the diameter of the opening is 10 centimeters. So this might not seem like a very important part of information, but it really is. We're seeing a relationship between the height of the container and the diameter of the container. Notice that the height is equal to the diameter. So if we start talking about radius, because that's what my formula gives me, then I know that the height is 2 times the radius. Or so we know that the radius is half of the height, isn't it? So we can go on and say, well, I know 1/2 h equals my radius. So that's important information, but it would be so easy to skip right over that. Water in the container is evaporating so that its depth is changing at this constant rate. So here's another small piece of information that we could very easily skip over that we don't need to, and that is that dH dt is -3/10. So we need to remember that. So for part A, you just need to find the volume of the water in the container. Let's see, find the volume when the height is 5 centimeters, and we need to indicate our unit of measure, which is always important for us to do. So we have our volume formula. So let's go ahead and plug in and see what all we know. We know volume equals, and we have 1/3 pi times our radius squared. Now, we were not given the radius, but we know a relationship between the radius and the height. So the radius was half of the height, and we're told that the height is 5, so the radius is 5/2 squared, because the formula squared, times the height, which is 5. So if we work out all of this, 5 squared, 25. 25 times 5, 125. And we do have pi here over 3 times 4. Remember, that is 2 squared, so over 12. And we need to indicate our unit of measure. So let's go back up and see, well, what were our units? And let's see, we had centimeters, didn't we? So here it's going to be the volume centimeters cubed. Okay, so now part B wants us to find the rate of change of the volume of water in the container with respect to time when the height is 5. And so again, notice we have our volume problem, and we're looking for the rate of change of the volume. So I'm looking for a dV dt. Let's see if I can squeeze that down here. I should have left more room. And notice our formula. And again, we do have R and H that we would need the product rule. But again, we're told that we do have a nice little relationship between the height and the radius. The radius is 1/2 the height. And so I would make that substitution because I already know dH dt is sitting right here. And so I would want to get away from having so many variables if I could help it. So here I would know that the volume is and I'm just going to plug in right quick before I do the derivative. I have 1/3 pi, and if I know the radius is half of the height and I square that, so that's going to give me h squared over 4 times h. So it looks like I can rewrite my volume then to be 1/12 pi h cubed. And so that's going to make that a lot easier to find the derivative of. And so let's see, dv dt equals, and I'm going to find the derivative of this problem here because it's the same exact thing. It's just written in terms of our height, so it make it a little bit easier for us. So that's going to be 3 times 1/12, so that's going to be 1/4 pi. So we've got pi over 4, or 1/4 pi, h squared times dh dt. So now I can plug in. So I have pi over 4 times our height, which is given to us, so that's going to be 25, times, let's see, the rate of change of our height, which is -3/10 centimeters per hour. So that's going to be our rate of change of our volume. And so we do need to remember that we need to talk about our units here. So let's see, we don't have to necessarily worry about multiplying all that information out. We found the derivative, we've plugged in, and then we can go ahead and say, well, that's centimeters cubed per hour. And that's going to be a rate of change of our volume. And that's really all we have to do for that one. Do remember, as far as assigning points, and I meant to tell y'all this in class, this part A, they awarded for this being complete, including your units and such, this part A was 1 point. And believe it or not, this B part, because there was so much going on in the problem, they awarded 5 points here, which is huge in one problem. So if you still are not sure about this question, please ask me about it in class. I will be happy to help you. Okay, another classic related rates problem. Here we have a ship, and ship A is traveling due west toward the lighthouse. So here we need to think about we're traveling toward the lighthouse. So here we're probably going to see a negative rate of change going on there because our distance, notice that distance is shrinking. So we should be slowing down, or they're just going to smack straight into the lighthouse. It would make sense that they need to slow down. And then what about ship B? Is traveling due north away from the lighthouse. So they're probably gaining speed there, one would think. So ship A, we're told that we have 15 kilometers per hour. And so here I would call that a D, -15 kilometers per hour, and that's our dx dt. Ship B traveling north away from the lighthouse at a speed of 10 kilometers per hour. So I would call that our dy dt. And what was that one? It was 10 kilometers per hour. Let's see, let x be the distance between ship A and the lighthouse rock at time t, and y be the distance between the ship B and the lighthouse rock at time t. And so for part A, it wants us to find the distance in kilometers between ship A and ship B when x is 4 kilometers and y is 3 kilometers. So we know this is going to be a 3, 4, 5 right triangle, but we have to find that distance, and so we do need to show our Pythagorean theorem. So we would label this side, this other side, z, and so we know our x squared plus our y squared equals z squared. And so we're going to have 4 squared plus 3 squared equals z squared. And I think from there it's safe to say that z is going to be 5 kilometers. And they awarded 1 point there for that answer. Okay, now they want for part B to find the rate of change in kilometers per hour of the distance between the two ships when x is 4 and y is 3. So here we need to find the derivative and plug in. And here, to ensure that you get your full points, I would make sure I show the 2's here and then go back and delete them out. That way they know you found the derivative correctly. And so here we have 2x dx dt plus 2y dy dt. And I think by now y'all probably almost have this memorized. 2z dz dt. And now in this case, remember dz dt is not going to go to 0. That's how the distance is changing between ship A and ship B. So we need to be careful with that. Now over here in the plugging in, I would go ahead and drop those 2's. Those aren't necessary. And so notice they told us x was 4 kilometers. So we have 4 times our rate of change, which was negative 15, plus y was 4 times that rate of change, which was, I think, 10. And let's see, y was 3, wasn't it? Oops, let's go back and fix that. So, well, if I can find the eraser, that would be useful. So let's go back and fix that. Sorry, guys. So we had 3 times 10, and that's going to be equal to 5 times dz dt, which is what we're trying to find. And hopefully when you figure out all of this, it looks like we're probably going to be equal to, let's see, we're going to do some little algebra magic here and put together and divide by 5. I think we end up with negative 6 for our rate of change. Negative 6, and we need our units, so that's going to be kilometers per hour. Okay, now let's see, we're going to have to squeeze in for part C. We're going to find the angle. Let's let theta, we're going to find the rate of change of the angle again. Yay, we had one earlier like this. So theta is the angle shown, and we need to find the rate of change of theta when x is 4 and y is 3. So let's look at, I know 3 and 4, but we need to have some kind of trig value, and I'm going to move this part C up to this corner so it makes it a little bit easier for us to have room. So for part C, we need to find the rate of change of theta. So let's see, from theta's point of view, and I need to change colors so we don't have so many colors going on here, or so much of one color. So here's theta. We know opposite and we know adjacent. So we're going to call this tangent of theta is going to be equal to y over x. And then after we do y over x, then we have our formula that we can find the derivative of, and we're going to have to use our quotient rule. So let's see, the derivative of tangent, I think that's secant squared theta. Now don't forget, times d theta dt is equal to, and then we do our bottom times the derivative of the top. Uh-oh, I bumped something. Sorry. Times, let's slide this over a little bit so I won't be running into everything. Okay, so bottom times the derivative of the top, so dy d theta, or dt, sorry, minus top times the derivative of the bottom, dx dt, all over bottom squared. So all over x squared. Now secant squared of theta, well, let's see. Let's go back to our triangle and look at what we know as far as sides. And I'm going to get rid of some of this over here. It's a lot of writing here. So I'm going to remove some of this. Let's see. We were told that x is 4. So I know this side's 4. We know that y is 3. And we know this other side here is 5. So secant of our angle, let's do secant of the angle first. Secant is going to be the reciprocal of cosine. And if cosine was 4 over 5, then secant is going to be 5 over 4. And that's going to be all squared times d theta dt, which is what we're looking for. That we don't know. That's the great mystery, d theta dt. Okay, equals, and let's see, we've got to figure out this other side. So we have x times the rate of change of y, so that's going to be 40 minus y, which is 3, times the rate of change of x, which is negative 15, so that's going to be negative 45. So that's going to be a positive minus the negative, or positive 45, all over x squared, which is going to give us 16. So, goodness gracious. So we have 25 over 16. 25 over 16 d theta dt equals, and let's see, that's going to give me 85 over 16. And so to finish solving this, we're going to multiply both sides by 16 over 25. So let's see, d theta dt is going to be 85 over 25. And y'all don't worry about reducing that. It's quite okay to leave it like that. And my goodness, if you got lost in the sauce on this problem, we do need our units. Right there it tells us it's radians per hour. So we're going to have rad per hour. This problem was worth, let's see, it was worth 4 points, as well as part B. So this was a great problem. That would have been 4 points, and this also 4 points. And do remember, it's not all or nothing. You would have gotten quite a bit of points for setting up tangent of theta as y over x and finding the derivative. That would have been another huge part of the problem. Finding the 85 over 25 would have just been a small portion of it. So don't feel like it's all or nothing. It's definitely not. All right, so now we have a coffee pot. Yay, we have coffee. Coffee problems are awesome. And let's see, we have the shape of a cylinder. We know what the radius is. The radius is 5 inches, so we've got that. All right, all right. I had to throw that in there. H be the depth of the coffee pot measured in inches. H is a function of time measured in seconds. The volume of the coffee pot is changing with the rate of, so that right there is our dV dt. That's important to know. And let's see, for part A, we need to show that dH dt is equal to negative square root of h over 5. Well, sure, everybody knows that it is, right? All right, let's see. We know the radius. I know the volume formula. Now, notice I'm just needing to pinpoint the rate of change of height. So I would go ahead, because this radius is 5 inches. The radius of that cylinder is really not going to change. It's going to be 5 inches no matter where you're at on this, because it's a cylinder. It's not talking about that inverted cone where the radius actually does change in length. The radius is not going to change. The radius will be the same here as it is here, as it is down here. So it's safe to say that that radius value is pretty much well fixed. So I would plug that in already to this volume formula. And so that tells me that volume equals see, 5 squared, so 25 pi times the height. So what else are we given? dv dt. I need to find the rate. So I need to find the derivative here with respect to time. So the derivative of v is 1 dv dt equals, let's see, there's that 1 exponent multiplied down. So that's going to be 25 pi. And then let's see, and then dh dt. Hey, there's what we need, dh dt. So I think we're probably getting a little bit closer, and that was a pi there. We know the rate of change of the volume. We were given that, so let's plug in. So I have negative 5 pi square root of h equals 25 pi dh dt. And again, remember, we're trying to prove dh dt is negative square root of h over 5. So yeah, I think we're about there. We need to divide both sides by 25 pi. Divide by 25 pi. And notice, all of this stuff is going to just very nicely go away, cancel. So I am left with negative square root of h over 5 equals dh dt. So there we've shown it. Now, I must have been on crack when I made this problem, or cropped this problem for y'all, because we don't know yet how to do B or C. So I guess I was just cracking it out on that one. Okay, for our problem on this packet. And this one also, I must have been on crack big time, because we don't know how to do A or B yet. So we're going to focus on part C. In part C, the funnel contains liquid that is draining from the bottom. At the instant when the height of the liquid is 3 inches, the radius of the surface of the liquid is decreasing at a rate of, so my goodness, we have so much information there. And I'm going to do part C up here because it's just going to be easier. One more room there. So let's see, at the instant when the height of the liquid is 3, so I know h is 3 inches. The radius of the surface of the liquid is decreasing, so I know dr dt, and it's decreasing, so goodness, that one I would think is probably negative, and what was it, 1/5? Okay, inches per second. At this instant, what is the rate of change of the height of the liquid with respect to time? So I'm looking for dh dt. That one, like, well, I don't know. Well, let's go back up and look at what we were given. And we were given this formula right here. That's what we've got. And really, that's all we need, because we're just given the rate of change of the radius. We want to know the rate of change of the height. We're given what an h value is. So I would rewrite r. And a lot of kids missed this problem last year or year before last. But let's rewrite this so that r equals, and let's use our good old distributive property. That's going to be 3 over 20 plus 1 over 20 h squared, isn't it? And the whole idea behind doing that is so that whenever I write out the derivative, well, it makes it a lot easier to work with. Let's see, if I find the derivative of that new r with respect to time, that's going to give me dr over dt equals, well, notice all of this, when I derivatize it, goes to 0. Well, yay. And then 0 plus, well, 2 over 20, or 1/10 h dh dt. And so now we plug in. We know dr dt is negative 1/5 equals 1/10 h. Well, h is 3. And I need to find dh dt. So let's see, what does it look like that's going to work out? 3 over 10 going to multiply by 10/3. So that looks like it's going to give me -10/15. And we need our rate, which is going to be, looking at the problem, inches per second, equals dH dt. And so we found it. And this problem, they awarded 3 points. And I know 3 points may not sound like a whole lot, but if you've taken an AP exam, you know 3 points is quite a bit. I hope this helps, and if y'all have any other questions about these problems, please ask me or post a question.